We'll start in a minute. Today we'll continue in section 8.3 on inverse trigonometric functions, and then afterwards we'll start section 9.1 on solving trigonometric equations with identities. Okay, yesterday we were working on these problems, and so we'll continue. Find the following sine, the sine of inverse cosine of 7/9. Okay, so the inverse cosine has a range between 0 and pi, and we know that sine is positive for, well, it's sine of 0 is 0 and sine of pi is 0, but in between 0 and pi, sine is positive. So we're expecting this to be a positive number, and we can use a right triangle. The angle whose cosine is 7/9. So this angle has a cosine of 7/9, and we just want to, since we want to take the sine of that angle, we need to know what the length of the opposite side is. So we can use the Pythagorean Theorem. 9 squared equals b squared plus 7 squared, or 81, and then subtract 49 from both sides, equals b squared. And we get 32 equals b squared. So we take the positive square root. B is equal to the positive square root of 32, which is simplifies to 4 times the square root of 2. Okay, so 4 times the square root of 2 is the length of the opposite side. So the sine of that angle is equal to 4 times the square root of 2 over 9. Okay, in the next example, the inverse, we want to find the value of sine of inverse tangent of 12/5. The range of inverse tangent is from negative pi over 2 to pi over 2, but when the tangents are positive, that will be between 0 and pi over 2. And sine is positive between 0 and pi over 2, so we're expecting the final answer to be positive. And once again, we can use a triangle. So the tangent, we want to find the sine of the angle whose tangent is 12/5. So here's the angle, and the tangent is opposite over adjacent. So now we have to use the Pythagorean theorem to find the hypotenuse. So the hypotenuse squared is equal to 12 squared plus 5 squared. 144 plus 25 is 169. And we want the positive square root, so the square root of 169 is exactly 13. Okay, so the sine of that angle is opposite over hypotenuse, so this is 12/13. Okay, then the cosine of the inverse tangent of 4/7. So once again, if the inverse of tangent is 4/7, then it's an angle between 0 and pi/2 because tangent is positive for those values. And so cosine will also be positive in the first quadrant. So again, use a right triangle. The angle whose tangent is 4/7, that's this angle. If the tangent is 4/7, the opposite side is 4, the adjacent side is 7, and we need to find the hypotenuse again, and we can do that using the Pythagorean Theorem. H squared equals 7 squared plus 4 squared, or 49 plus 16, and 49 plus 16 is 65. So we want h equals the positive square root of 65. And so the cosine of that angle is adjacent over hypotenuse, 7 over the square root of 65. Okay, we'll look at some more exercises. Find the exact values. In the first row, we have all inverse sine. Arc sine is just another way to write the inverse sine. So I'll remind you the domain for the inverse sine function are the numbers from -1 to 1, including -1 and 1. And the range, or the output values for inverse sine, are from -pi/2 to pi/2. Okay, so the inverse sine of -√3/2, this has to be equal to a negative angle. It has to be something from -pi/2 to 0. We do know that the sine of pi/3 is positive square root of 3/2. So this is just going to be the negative of pi/3, or -60 degrees, if you want to think of it in terms of degrees. Okay, the arc sine of -1, or the inverse sine of -1, well, the angle whose sine is -1 is -pi/2. Or you could write -90 degrees. Okay, the inverse sine of -3. Well, the domain of inverse sine is from -1 to 1. So this domain value, well, it's not in the domain, so this is undefined. Okay, now let's look at some inverse cosines. So for inverse cosine, the domain is also from -1 to 1, but the range of inverse cosine is from 0 to pi. It's on that interval that the cosine function is 1 to 1, so its inverse has a range from 0 to pi. Okay, the inverse cosine of -1/2. We know that cosine is positive from between 0 and pi/2, and cosine is negative between pi/2 and pi. So this has to give us an angle that's between pi/2 and pi. We do know that cosine of pi/3 is 1/2, and so cosine of 2 pi over 3 is negative 1/2. So the inverse cosine of negative 1/2 is 2 pi over 3. Okay, the arc cosine of the square root of 2 over 2. The angle whose cosine is the square root of 2 over 2 is pi over 4, or 45 degrees. Over here, this one, 2 pi over 3, is equivalent to 120 degrees. Okay, the inverse cosine of negative 1. The angle that has a cosine equal to negative 1 is pi, because cosine of pi is negative 1. Or you could write 180 degrees if you want. Okay, now let's do some examples involving inverse tangent. So for inverse tangent, the domain is all real numbers from negative infinity to positive infinity, and the range of inverse tangent is strictly between negative pi over 2 and pi over 2. Okay, so the inverse tangent of negative square root of 3 over 3 has to be an angle between negative pi over 2 and 0, because tangent is negative between negative pi over 2 and 0. So we know that the tangent of pi over 6 equals negative square root of 3 over 3. So this is going to be equal to the negative pi over 6. Or negative 30 degrees. Okay, the arctangent of negative 1. The angle whose tangent is negative 1 is negative pi over 4, or equivalently negative 45 degrees. And then the last one here, the inverse tangent of the square root of 3. Well, we know that the tangent of pi over 3 is equal to the square root of 3. So that's what this is equal to, pi over 3, or 60 degrees. Okay, so make sure you practice those. One thing that's nice is that either at least in these examples, the angles are special angles, or angles whose reference angles are special angles. Okay, let's look at another exercise. So here we're given that cosine of theta is equal to negative 8/11, and theta is between 180 degrees and 270 degrees. So that's in the third quadrant. And we're also given that the inverse cosine of negative 8/11 is approximately 136.7 degrees. Okay, so this angle is in the second quadrant. So if we sketch this, 136.7, so it's right in here somewhere. So 136.7 degrees. But we want to find the angle theta in the third quadrant down here, such that the cosine of theta is equal to negative 8/11. So we have this angle in the third quadrant, I'll sketch in what theta has to be. Theta in standard position counterclockwise goes to there. Okay, well, it turns out that we can use the reference angle of the reference angle to 136.7. So 136.7 plus the reference angle has to add up to 180 degrees. So this reference angle is 43.3 degrees. 43.3 degrees. And the theta that we want, well, my graph doesn't look like it, but this reference angle has to be the same as 43.3 degrees. So the theta that we want is 180 degrees plus 43.3 degrees. 180 degrees plus 43.3 degrees. Do the arithmetic, we get 243.3 degrees. So the purpose of this exercise is to show you that if you just take the inverse cosine of both sides of this equation, you won't get the right angle because we're given that this angle theta is between 180 degrees and 270 degrees. Okay, another example along the same lines. The tangent of theta is equal to negative 9/7, and theta is between pi over 2 and pi. So this is in the second quadrant. But the range of inverse tangent is from negative pi over 2 to pi over 2. So the fourth quadrant and the first quadrant. So we can draw a picture to help again. So we want tangent of theta equals 9/7 in the second quadrant. Tangent is negative in the second quadrant. Okay, so something like this. This is our theta that we want. But inverse tangent is negative 9/7. The inverse tangent of negative 9/7 is negative 0.9098. So this angle, since it's negative, we move clockwise. And so this is the angle negative 0.9098 radians. And this angle, well, the reference angle is positive 0.9098. But the size of this angle, at least in absolute value, the sine of this angle, which is the reference angle to theta, is the same as this one. Okay, so how can we find what theta has to be using inverse tangent of negative 9/7? Notice that if we begin with inverse tangent of negative 9/7 and add pi to it, we end up with theta. So in other words, theta, which is in the second quadrant, that is equal to the inverse tangent of negative 9/7 plus pi. And we're told what this value is approximately. So we can write it, we can put pi first and then subtract 0.9098. That is the value of theta that we want in this case. Okay, so these problems that we've done these last several minutes, they take some thinking and some practice, so make sure that you do a lot of practice on these. Now we'll do some algebraic exercises involving some trig functions and inverse trig functions. So this says find the exact value of the expression in terms of x. Use a right triangle as a reference. Okay, so we want to find the sine of inverse cosine of 1 minus x. Okay, so if we use a right triangle to help, the inside function, inverse cosine of 1 minus x. So this is the angle whose cosine is 1 minus x. So the cosine of this angle, the adjacent over hypotenuse, is 1 minus x over 1, or 1 minus x. So we want to find the sine of this angle, so that means we need to find this opposite side over here. I'll call it A for now. Then we use the Pythagorean Theorem to determine what A is. So 1 squared equals 1 minus x squared plus A squared. And then when we square 1 minus x, we get 1 minus 2x plus x squared plus A squared. And then I'll write A squared equals, we'll subtract 1 from both sides, add 2x, subtract x squared. So when we do the algebra and arithmetic, we're just going to be left with 2x minus x squared. And so A is the square root of 2x minus x squared. That's the opposite side, square root of 2x minus x squared. And the sine of that angle is the square root of 2x squared, the square root of 2x minus x squared over 1, or just the square root of 2x minus x squared. Okay, we do the same sort of thing in the next exercise. Find the cosine of the inverse sine of 1 over x. Okay, so the inverse sine of 1 over x, that represents the angle. Here's the angle whose sine is 1 over x. So opposite over hypotenuse, 1 over x. And we want to find the cosine of that angle, so we still have to find the adjacent side. So let's call this side B momentarily. Use the Pythagorean Theorem. So the square of the hypotenuse is equal to the sum of the squares of the other two sides. And so subtract 1 from both sides. We get B squared equals x squared minus 1, and so B is equal to the square root of x squared minus 1. That's the adjacent side, square root of x squared minus 1. And so the cosine of that angle is adjacent over hypotenuse, which is the square root of x squared minus 1 over x. Okay, the next one, find the tangent of the inverse sine of x plus 1/2. Well, I think it's not required, but I think it makes it easier if we simplify the argument of inverse sine. Instead of x plus 1/2, let's write it as 2x plus 1, all over 2. You don't have to do it that way, but this, in my opinion, makes the algebra a little bit simpler. So we want to find the tangent of the angle whose sine is 2x plus 1 over 2. So if we construct the right triangle, the angle whose sine is 2x plus 1 over 2, opposite over hypotenuse. So now we need to find the length of the adjacent side in terms of x. So again, we use the Pythagorean theorem. So we square the length of the hypotenuse, 2 squared, and that's equal to c squared plus the binomial 2x plus 1 squared. So 2 squared is 4, and we're going to subtract what we get when we square the binomial 2x plus 1. So we're going to subtract 4x squared, and we're also going to subtract 4, and we're also going to subtract 1. So that's equal to c squared. So when we simplify this, we get negative 4x squared minus 1 equals c squared. So we take the square root, negative 4x squared minus 1. Okay, so the tangent of that angle then is opposite over adjacent. Okay. The next one, given that sine of t is x over x plus 1, find cosine of t and cotangent of t. So this is the same sort of thing. Sine of t, so here's the angle t. The sine of t is x over x plus 1. And in order to find the cosine of t and cotangent of t, we need to know what the adjacent side is. So let's call the adjacent side A for now, and then use the Pythagorean theorem. When we square x plus 1, we get a squared plus x squared. So the left-hand side is x squared plus 2x plus 1 equals a squared plus x squared. And when you subtract x squared from both sides, I'll write a squared on the left. A squared equals 2x plus 1. And so a is the square root of 2x plus 1. That's the adjacent side, square root of 2x plus 1. So now we can write down the cosine of t. Cosine of t, the adjacent side, square root of 2x plus 1, over the hypotenuse x plus 1. And then the cotangent of t, well, that's adjacent over opposite. So the adjacent side has length square root of 2x plus 1, and the opposite side is x. Okay, a couple more thinking examples. Find the exact values. Find the sine of the inverse cosine of negative 3/7. Okay, remember what the range of inverse cosine is. The range of inverse cosine is from 0 to pi. And so the inverse cosine of a negative number has to be between pi over 2 and pi. But sine, if the number is between pi over 2 and pi, sine of that number is positive. So the end number has to be positive for this one. So we can just construct an ordinary right triangle, or we can also recognize that inverse cosine of a negative number has to be in the second quadrant. So this angle is the inverse cosine of negative 3/7. So we can construct a right triangle. The adjacent side is negative 3 and the hypotenuse is 7. And we want to find, in order to compute the sine of that angle, we need to know what the opposite side is. So let's call it B. So the hypotenuse is 7, so 7 squared equals B squared plus the number negative 3 squared. So 7 squared is 49, and we're going to subtract 9, so we get 40 equals B squared. And so B is equal to the positive square root of 40, which is 2 times the square root of 10. And so the sine of that angle is the opposite side, 2 times the square root of 10 over the hypotenuse 7. So this is what sine of the inverse cosine of negative 3/7 is. Okay, we do the same sort of thing over here. Find the cosine of the inverse sine of negative 2/11. Remember that the range of inverse sine is from negative pi over 2 to pi over 2. But negative pi over 2 to pi over 2, that's the fourth and first quadrant. And cosine is positive in the fourth and first quadrant. So this number has to be positive. So this angle, the angle whose sine is negative 2/11, is between negative pi over 2 and 0. So negative pi over 2 to 0 is in the fourth quadrant. So let's construct an angle, something like this. This is our angle. The hypotenuse is 11, and this opposite side is negative 2. But we just have a right triangle. So we want to know what the adjacent side is. The hypotenuse is 11, so 11 squared equals a squared plus negative 2 squared. 11 squared is 121. And when we subtract 4, we get 117 equals a squared. And so a will just be the positive square root of 117. Okay, so the cosine of this angle is the inverse sine of negative 2/11. It's the adjacent side, the square root of 117 over the hypotenuse 11. Okay, the next couple of problems will be a little bit easier in comparison. A little bit. This one, write the expression below as an algebraic expression for values of x greater than 4. So compute the tangent of the inverse sine of the square root of x squared minus 16 over x. So we'll use a right triangle to help us. So here's the angle that represents inverse sine of the square root of x squared minus 16 over x. Okay, so the angle whose sine is the square root of x squared minus 16 over x, that is, the opposite side is the square root of x squared minus 16, and the hypotenuse is x. The sine of this angle is the square root of x squared minus 16 over x. That's what this represents here. And we want to find the tangent of that angle, but that means we need to find the length of this side in terms of x. So let's call it, oh, I don't know, how about d? No particular reason. Let's find what d is using the Pythagorean theorem. So square the hypotenuse, x squared equals d squared plus the square root of x squared minus 16 squared. So when we square the square root of something, we just get the something. So the square root of x squared minus 16 is x squared minus 16. So we'll subtract x squared from both sides and add 16 to both sides. We find that d squared equals 16. And so d is equal to positive 4. D is 4. Okay, so the tangent of the angle then is the square root of x squared minus 16, square root of x squared minus 16 over 4. Okay, the next exercise, this will be the last one for section 8.3. A downhill path is 1,250 yards, and the altitude difference from the top to the bottom is 480 yards. Find the incline angle. Okay, so we have a downhill path. We'll assume it's straight downhill, and it's 1,250 yards. The altitude difference from the top to the bottom is 480 yards. So the difference from the top to the bottom in altitude is 480 yards. And we want to find the incline angle. Let's call it theta. That's the incline angle. Well, in this case, since in this right triangle, with respect to theta, we know the opposite side, the length of the opposite side, and the hypotenuse. So we could just say, well, sine of theta is 480 divided by 1250. You could simplify that a little bit and write it as 48 over 125 if you want. And then the incline angle is between 0 and pi over 2. So the inverse sine of theta, or the inverse sine of 48 over 125, all I did was take the inverse sine of both sides of that equation. The inverse sine of sine theta is theta, and then that's equal to the inverse sine of 48 over 125. So for these exercises, use a scientific calculator if you want to come up with an actual number that you can relate to. So use a scientific calculator. When you're practicing these. Okay, now we'll move on to section 9.1. Well, we will review some identities to start with. The Pythagorean identities, sine of theta squared plus cosine of theta squared equals 1. And I'll remind you how the other two can be derived. If we divide every term on both sides of this first Pythagorean identity by sine of theta squared, we get this one. So I'll go through the motion. Sine of theta squared divided by sine of theta squared plus cosine of theta squared divided by sine of theta squared equals 1 divided by sine of theta squared. So when you simplify this, you get this Pythagorean identity. Okay, for the next one, I won't write it down, I'll just mention if you divide both sides of this Pythagorean identity on the left, if you divide every term on both sides by cosine of theta squared, then you get this identity. Okay, remember that the sine function is an odd function, and so is the reciprocal function cosecant. Sine and cosecant, sine and cosecant are both odd functions. Cosine is even and its reciprocal is even. Both tangent and cotangent are odd functions. So whenever you see sine of negative theta, if you prefer, you can write it as negative sine of theta. The same goes for the reciprocal function. Cosecant of negative theta equals the negative of cosecant of theta. And then it's also important and very useful to remember that cosine of negative theta equals cosine of theta. And the same is true for the reciprocal of cosine. Secant of negative theta equals secant of theta. Tangent and cotangent are odd functions, so tangent of negative theta equals negative tangent of theta. Cotangent of negative theta equals negative cotangent of theta. So the next couple of problems, the first part here, show graphically that y equals sine of x is an odd function. Okay, so if we sketch a graph of a couple of periods of sine, so do the first period on the right to start with. And then the period on the left. So the input values, well, 0, this one's pi over 2. pi, 3 pi over 2, and 2 pi. Then this one's negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. So what does it mean graphically for a function to be odd if y is a function of x? Then what does that mean? What that means is that the graph is symmetric with respect to the origin 0, 0. So the idea is if I draw a straight line through the origin, kind of like this, pretend like that's a straight line, then the distance from the origin to this point on the graph will be the exact same distance from that point to the graph in the opposite direction. So this distance from there to there is equal to this distance from there to there. That will be true for any point on the graph of an odd function. That's what it means to be symmetric with respect to the origin, the point 0, 0. Okay, so graphically that y equals cosine of x is an even function. So I'll just do, oh, I guess we can do the whole thing. Okay, so a graph of y equals cosine. There's one period to the right, another period to the left. So the input values, so negative 2 pi, negative 3 pi over 2, negative pi over 2, 0, pi over 2, pi, negative 3, sorry, not negative, 3 pi over 2, and 2 pi. Okay, so what does it mean graphically for a function to be even? Well, it means that the graph is symmetric with respect to the y-axis. So the y-axis is like a mirror. It reflects the graph that's on the right, and it reflects it exactly to the left. Another way to interpret that is if you draw a horizontal line, and if the horizontal line intersects the graph on the right side of the y-axis, then it also must intersect the graph the same distance to the left of the y-axis for a horizontal line. Okay, we've seen these reciprocal and quotient identities, but doesn't hurt to go over them. Sine of theta is 1 over cosecant of theta. And likewise, cosecant of theta is 1 over sine of theta. Tangent of theta is sine of theta over cosine of theta. Cosine of theta, its reciprocal function is secant theta. So cosine of theta is 1 over secant of theta. And secant of theta is 1 over cosine of theta. And cotangent of theta is cosine of theta over sine of theta. Tangent of theta is 1 over cotangent of theta, and cotangent of theta is 1 over tangent of theta. So hopefully those are very familiar to you by now. Okay, we're going to use fundamental identities to completely simplify the expressions. So in these exercises, instead of using theta, we're using x, but that's not a problem. So the key here is use fundamental identities to completely simplify the expressions. Okay, so tangent of theta, we'll write that as, tangent of x is sine of x over cosine of x. And we're multiplying that by sine of x. And so I'm going to write that as sine of x over 1, just for clarification. Secant of x is 1 over cosine of x. And we're multiplying that by cosine of x squared over 1. There's a couple of things that could happen, but in my opinion, the most straightforward thing to do is notice we're adding those two terms and they both have a common denominator, or they both have the same denominator of cosine of x. So let's just write it as a single rational expression with cosine of x in the denominator. And then sine of x times sine of x is sine of x squared. And we're adding that to 1 times cosine of x squared. And in the numerator, sine of x squared plus cosine of x squared is 1. So we have 1 over cosine of x. And we can write this more compactly because 1 over cosine of x is secant of x. So that expression simplifies to secant of x. Okay, and the next one, just a comment about simplifying trigonometric expressions. Oftentimes, if you can convert what you're looking at in terms of sine and cosine, oftentimes that will lead you to what needs to be done next. So we can apply that in this next case. We have 3 times sine of t to the third times cosecant of t plus cosine of t squared plus 2 times cosine of negative t times cosine of t. So in the first step, I'll just leave 3 times sine of t to the third over 1. But then I'm going to replace cosecant of t with 1 over sine of t. And for now, I'll just leave cosine of t squared the way it is. And then we remember that cosine of negative t is equal to cosine of t. So I'll go ahead and write plus 2 times cosine of t squared. Okay, let's simplify this one. 3 times sine of t to the third over 1 times 1 over sine of t. 1 factor of sine of t cancels. So we're left with 3 times sine of t squared, and then plus, oh, I missed my chance. Oh well, I'll just rewrite what we have over here. Cosine of t squared plus 2 times cosine of t squared. And we can combine these, and we can write 3 times sine of t squared plus 3 times cosine of t squared. And you all know what that's going to be equal to. It's not really necessary, but I'll go ahead and factor 3 out of each of those terms. So we have 3 times the quantity sine of t squared plus cosine of t squared. And sine of t squared plus cosine of t squared equals 1. So 3 times 1 is 3. So that is just a fancy way to write the number 3. Okay, the next one on this one, I have a typographical error right in the middle where it says secant of s. Well, we want that to be x. Okay, the negative sign of negative x, remember sine of negative x is negative sine of x. So this is going to simplify to sine of x. So I'm going to divide the denominator, cotangent of x, with the numerator. In the denominator, cotangent of x is cosine of x over sine of x. And so since we have, in the numerator, we have sine, cosine, secant, cosecant, and tangent, I'm going to write each of those individually as fractions or rational expressions. So negative sine of negative x simplifies to sine of x over 1, and then times cosine of x over 1. Secant of x is 1 over cosine of x. Cosecant of x is 1 over sine of x. And then we'll multiply that by, instead of tangent of x, I'll write sine of x over cosine of x. Okay, we get a bunch of cancellations. This factor of sine of x from this numerator cancels with this one from the denominator, and also cosine of x divided by cosine of x, those cancel. Okay, so I'll just clean this up a little bit. We have sine of x over cosine of x divided by cosine of x over sine of x. And then in the next step, we'll divide the fraction in the numerator, or we'll multiply the fraction in the numerator by the reciprocal of the fraction in the denominator. So sine of x over cosine of x times sine of x over cosine of x. And we get sine of x squared over cosine of x squared. So we can write it as tangent of x squared. Okay, I see an easier way to do that one now. We could have just left tangent of x the way it was, and then we could have converted everything else into tangent of x, and then tangent of x times tangent of x is tangent of x squared. But as you have no doubt noticed, when simplifying trigonometric expressions, there are often more ways to go about it. Hey, this next one, simplify. So here we have 1 minus cosine of x squared over tangent of x squared plus 2 times sine of x squared. The thing that jumps out at me is in this numerator, 1 minus cosine of x squared. That's equal to sine of x squared. And then we're over tangent of x squared plus 2 times sine of x squared. So just to remind you, we know that cosine of x squared plus sine of x squared equals 1. So if you subtract cosine of x squared from both sides, you're just left with sine of x squared. So I'll go ahead and write it. Sine of x squared is equal to 1 minus cosine of x squared. That's where this comes from. Well, it looks like what needs to be done is convert tangent of x squared to sine of x squared over cosine of x squared. So we'll have sine of x squared over 1 divided by tangent of x squared written as sine of x squared over cosine of x squared plus 2 times sine of x squared. So here we are in effect dividing one fraction by another. So whenever you divide one fraction by another, you can multiply the first fraction by the reciprocal of the other fraction. And then plus 2 times sine of x squared. So we get a cancellation, sine of x squared divided by sine of x squared equals 1 and we're left with cosine of x squared plus 2 times sine of x squared, but I'm going to write that as sine of x squared plus sine of x squared. And then I'm going to replace cosine of x squared plus sine of x squared with 1. So I'm going to end up with 1 plus sine of x squared. So it looks to me that that's as far as this can be simplified. Okay, the next few exercises have more specific directions. This one says write tangent of x plus cotangent of x divided by cosecant of x in terms of cosine of x. Okay, so we'll see how that goes. So tangent of x, we'll start by writing it as sine of x over cosine of x. And we're adding that to cotangent of x, which is cosine of x over sine of x. We're dividing by cosecant of x, but we can write that as 1 over sine of x. Okay, so what I'll do next, instead of combining the sum in the numerator, I'm going to multiply the entire numerator by the reciprocal of 1 over sine of x. So this will be sine of x over cosine of x plus cosine of x over sine of x. And we multiply by the reciprocal of 1 over sine of x. So multiply by sine of x over 1. And when we distribute it, we get sine of x times sine of x, which is sine of x squared over cosine of x. And then when I multiply sine of x over 1 times cosine of x over sine of x, the sine of x factors cancel, so I just get plus cosine of x. And now we'll simplify this. The least common denominator is cosine of x. So if we multiply the numerator and denominator by cosine of x, we're just multiplying by 1. We'll get sine of x squared plus cosine of x squared divided by cosine of x. And then in the numerator, sine of x squared plus cosine of x squared is 1, so we get 1 over cosine of x. Well, according to the directions, we're just going to write that original expression in terms of cosine of x. So we'll just leave this as 1 over cosine of x. Okay, in the next example, write this difference in terms of cosecant of x. So we have 1 over 1 minus cosine of x minus cosine of x over 1 plus cosine of x. So the least common denominator is what we get when we multiply 1 minus cosine of x times 1 plus cosine of x. So if we multiply the expression on the left, 1 over 1 minus cosine of x, multiply that by 1 in the form 1 plus the cosine of x over 1 plus the cosine of x. And then we're going to subtract. So the original one is cosine of x over 1 plus cosine of x. We will also multiply this by 1, but the form that 1 takes for this one will be 1 minus cosine of x over 1 minus cosine of x. And now we just do the algebra and arithmetic. We'll have a common denominator. Okay, the common denominator is just the product of 1 plus cosine of x and 1 minus cosine of x. So let's do the denominator first. 1 minus cosine of x times 1 plus cosine of x, that's going to simplify to 1 minus cosine squared of x, or cosine of x squared. Okay, so this part of the numerator, 1 times 1 plus cosine of x is 1 plus cosine of x. And here's where you have to be careful. We're going to subtract cosine of x times 1, so minus cosine of x. But we're also going to subtract cosine of x times negative cosine of x. So we're subtracting negative cosine of x squared, which is equivalent to adding cosine of x squared. Okay, so this numerator simplifies to 1 plus cosine of x squared. And the denominator, 1 minus cosine of x squared, is sine of x squared. So just to harken back what we're trying to do, we're trying to write the original expression in terms of cosecant of x, which is the reciprocal of sine of x. So that was what I was focusing on when I replaced 1 minus cosine of x squared with sine of x squared, because I can write down, I can replace sine of x squared in terms of its reciprocal cosecant of x. But we have cosine of x squared. We can replace cosine of x squared with 1 minus sine of x squared. So I'm running out of space, but we have 2 minus sine of x squared over sine of x squared. And we're a couple of steps away. Since there's just one term in the denominator, we'll write it as 2 divided by sine of x squared, and then minus 1, because sine of x squared divided by sine of x squared is 1. And finally, we can write this in terms of cosecant. If I have sine of x squared in the denominator, that's equivalent to having cosecant of x squared in the numerator. So it simplifies to that. Yes, these identities might take some getting used to, so make sure that you practice a lot. Now we want to write this, 1 minus sine of x over 1 plus sine of x minus 1 plus sine of x over 1 minus sine of x in terms of secant of x and tangent of x. Okay, so the least common denominator is 1 plus sine of x times 1 minus sine of x. So similar to what we did in the previous example, we'll multiply each of the terms by 1 in special forms. So I'm going to multiply this term on the left by 1 in the form of 1 minus sine of x over 1 minus sine of x, and then we're subtracting again. And the term on the right, I multiply by 1, so 1 plus sine of x over 1 minus sine of x. The form that 1 takes this time is 1 plus sine of x over 1 plus sine of x. Now we have a common denominator, which is 1 minus sine of x times 1 plus sine of x. Okay, so let's just write the common denominator. When we multiply 1 plus sine of x times 1 minus sine of x, we get 1 minus sine of x squared. And then in the numerators, we'll multiply. So 1 minus sine of x times 1 minus sine of x. We're going to get 1 minus 2 sine of x plus sine of x squared. And then we have to subtract. We have to subtract the product we get when we multiply 1 plus sine of x times 1 plus sine of x. So I'll put that quantity in brackets, and then afterwards we'll subtract it. So 1 plus sine of x times 1 plus sine of x is 1 plus 2 times sine of x plus sine of x squared. Okay, so in the denominator, I'm going to replace that with cosine of x squared, since 1 minus sine of x squared is cosine of x squared. And then we'll do the arithmetic carefully up here. So we have 1 minus 1. So those cancel each other out. 1 minus 1 is 0. We have negative 2 sine of x minus 2 sine of x. So that leaves us with negative 4 sine of x. And then sine of x squared minus sine of x squared, those also cancel to 0. So now we're just left with negative 4 sine of x divided by cosine of x squared. Okay, so I'll put in one more spot here. Let's write this as negative 4 sine of x over one of the factors of cosine of x times 1 over cosine of x. Okay, then the negative 4 sine of x over cosine of x, that's negative 4 tangent of x. And then if I multiply by 1 over cosine of x, that's equivalent to multiplying by secant of x. Okay, so this is the final result. It's written in terms of secant of x and tangent of x. Okay, the next exercise, write cosine of x divided by 1 plus sine of x plus tangent of x. Write it in terms of cosine of x. Okay, so the first step, at least the way I would start it, I would replace tangent of x with sine of x over cosine of x. And the least common denominator is 1 plus sine of x times cosine of x. So we'll multiply cosine of x over 1 plus sine of x. We'll multiply that by 1 in the form cosine of x over cosine of x. Right, because the least common denominator is 1 plus sine of x times cosine of x. And then we'll multiply sine of x over cosine of x by 1 in the form of 1 plus sine of x over 1 plus sine of x. Now we have a common denominator. We have a common denominator. I'm going to leave it in factored form for right now. We'll have 1 plus sine of x. That quantity times cosine of x for the denominator. And then in the numerator, we have cosine of x times cosine of x, which is cosine of x squared, and then plus sine of x times 1 plus sine of x, so we have plus sine of x plus sine of x squared. The cosine of x squared plus sine of x squared is 1, so we can just write this as 1 plus sine of x. And in the denominator, we have the factor 1 plus sine of x times cosine of x. So 1 plus sine of x divided by 1 plus sine of x is 1. So we get 1 divided by cosine of x. Since we were supposed to write that in terms of cosine of x, then we leave it as 1 over cosine of x. Okay, we still have even more to do. This will be a little more challenging because it says to prove or disprove. If you can use algebra like what we've been doing and show that one side is eventually shown to be equal to the other, then that's how you prove an identity. To disprove an identity, all you need is one counterexample. So in other words, if you suspect that the equation is not an identity for all values of x, you can pick a specific x value and replace every x with that angle or input number. And if you get an equation that's false, then that's how you disprove that an equation is an identity. But sometimes you need to carry out a simplified process before you begin to suspect that it might not be correct. So we'll do that to start with. So first, notice in this denominator, we have 1 minus cosine of negative x. But cosine of negative x is cosine of x. So I'll just rewrite 1 over 1 plus cosine of x minus 1 over 1 minus cosine of x. Typically, when proving that an equation is an identity, usually we begin with one side or the other and simplify it as much as you can and try to show that it's equal to the other side. So I'm going to begin with the left-hand side and simplify it, and then I'm going to see if I can get it to equal negative 2 times cotangent of x times cosecant of x. Okay, so we'll get a common denominator. The least common denominator is 1 plus cosine of x times 1 minus cosine of x. So if we multiply this numerator by 1 minus cosine of x, and then you always have to be careful with subtraction. We're going to subtract this numerator when we multiply it by 1 plus cosine of x. And then the common denominator is 1 plus cosine of x times 1 minus cosine of x. Okay, so now we'll simplify what we can. We have 1 minus 1, so the 1's cancel each other out. 1 minus 1 is 0. But then we have negative cosine of x minus cosine of x. So that's negative 2 cosine of x. And in the denominator, we've seen this today. 1 plus cosine of x times 1 minus cosine of x is 1 minus cosine of x squared. And notice where we're trying to get to. We're trying to get to negative 2 cotangent of x cosecant of x. Cosecant of x is the reciprocal of sine of x. So that is a motivating factor to replace 1 minus cosine of x squared with sine of x squared. So we'll write this as negative 2 cosine of x divided by sine of x squared. Okay, well now we're just a couple of steps away. Negative 2 cosine of x divided by sine of x squared, we can think of that as negative 2. I'll put negative 2 over 1 times cosine of x over one of the factors of sine, so sine of x, and then times 1 over sine of x. So you can tell that what I just wrote is equivalent to where we started from on the left. But now we can write the punchline. We have -2 cosine of x divided by sine of x is cotangent of x, and 1 over sine of x is cosecant of x. So we proved that this equation is an identity. Okay, the next one, prove or disprove. Cosecant of x squared times 1 plus sine of x squared equals cotangent of x squared. So I'm going to start by writing that cosecant of x squared is 1 over sine of x squared. And then I'll multiply that by the quantity 1 plus sine of x squared. So 1 over sine of x squared times 1 is 1 over sine of x squared. 1 over sine of x squared times sine of x squared is 1. And I'm going to rewrite this as cosecant of x squared plus 1 equals cotangent of x squared. Sorry. We're investigating now. Is this true? Well, this kind of looks like one of those Pythagorean identities, but it's not exactly the same. So we can remind ourselves, if we begin with sine of x squared plus cosine of x squared equals 1. So if I divide both sides by sine of x squared, I get 1 plus cotangent of x squared equals cosecant of x squared. Okay, this is the real identity, but this is not the same as that. So we suspect that this is not a true identity. Suspect. Okay, so let's see if we can pick a value that we can replace x with. So let's see, how about so cotangent is, okay, so how about pick x equals pi over 2. So on the left, cosecant of pi over 2 squared times 1 plus sine of pi over 2 squared. This is the left-hand side. Well, cosecant of pi over 2 squared is the same as 1 over sine of pi over 2 squared. But sine of pi over 2 equals 1, so 1 over 1 is 1. So this, we have 1, and then times 1 plus 1 squared. So the left-hand side is equal to 2. And then the right-hand side, cotangent of pi over 2 squared, that's cosine of pi over 2 squared over sine of pi over 2 squared. Well, cosine of pi over 2 is 0, so 0 squared is 0. And 0 divided by 1 is 0. Okay, so it's true that 2 does not equal 1, so that means this is not an identity. This is not an identity. I don't know for sure, but my suspicion is that whoever came up with this problem did so in an attempt to make you think that you were looking at an identity that is not really an identity. Okay, let's move on to the next one. 1 plus sine of x over cosine of x. Does that equal cosine of x over 1 plus sine of negative x? Remember that sine of negative x is negative sine of x. So if you want to rewrite the identity with that simplified, you could. On this one, one way to go about checking to see if this is an identity, if this equation is true, then cross products are equal. So one cross product is 1 plus sine of x times 1 minus sine of x. We want to know if that's equal to the other cross product, cosine of x times cosine of x. So 1 plus sine of x times 1 minus sine of x is 1 minus sine squared of x equals cosine of x squared. And we know that that's true. So this is an identity. Okay, this next one. Let's write we'll start on the left-hand side, and sine of negative x is negative, so I'll bring a negative out front. And write this as negative tangent of x. If you have secant of x in the denominator, that's equivalent to cosine of x in the numerator. And then sine of x. So rewrite tangent as negative sine of x over cosine of x times cosine of x times sine of x. The cosines cancel, and we're left with negative sine of x squared. So I simplified the left-hand side, and I got negative sine of x squared. And we know that that does not equal cosine of x squared. So this is not an identity. You could pick x to be 0. Secant of 0 is 1, so we're not dividing by 0. Tangent of 0 is 0, so 0 divided by 1 times 0. Cosine of 0 is 1, so this is not an identity. Not an identity. Okay, we will at least get as far as we can on this last page. Verify each identity. This time we're told that they're all identities, so. But maybe you shouldn't always be so trusting. Anyway, on the left, if we start on the left, we'll factor cosine of x out of both terms. So we get cosine of x times 1 minus cosine squared of x. And then 1 minus cosine of x squared is sine of x squared. So we get cosine of x times sine of x squared. And that's exactly the right-hand side, so we're done. So that took, what, like 1 step or so. Okay, and the next one, we'll begin on the left-hand side. So when we square sine of x plus cosine of x, we get sine of x squared plus 2 sine of x times cosine of x plus cosine of x squared. The sine of x squared plus cosine of x squared, that's 1. So we get 1 plus 2 times sine of x times cosine of x. And this is the right-hand side already. So we're done. Okay, the next one. So we have secant of negative x. Secant is even, so secant of negative x is equal to secant of x. But I'm going to rewrite secant of x as 1 over cosine of x. And then in the denominator, tangent of x, I'll write that as sine of x over cosine of x. And cotangent, I'll write that as cosine of x over sine of x. And then 1 over cosine of x. Down here, we want a common denominator. So the common denominator will be cosine of x times sine of x. And so in the process, we have to multiply sine of x by sine of x. So we get sine of x squared. And we have to multiply cosine of x by cosine of x. So we get cosine of x squared. So 1 over cosine of x. We know that sine of x squared plus cosine of x squared is 1. So I'm just going to multiply the fraction in the numerator by the reciprocal of this. So the reciprocal is cosine of x times sine of x over 1. The cosines cancel, and we're left with sine of x. But sine of x is equal to the negative of sine of negative x. So that's what was required on the right-hand side. Okay, one more. Show that 3 times sine of x squared plus 4 times cosine of x squared equals 3 plus cosine of x squared. Well, let's just write 3 times sine of x squared. I have a total of 4 cosine of x squared, so I'll take 3 of those, 3 times cosine of x squared, and then add the other one, the other cosine of x. Out of the first 2 terms, we can factor 3 out, so we have 3 times sine of x squared plus cosine of x squared plus cosine of x squared. And sine of x squared plus cosine of x squared is 1, so we're just left with 3 times 1 plus cosine of x squared. We ended up with what we were supposed to. So that completes that. So I ran out of problems to do for today, but it looks like we have less than 1 minute left. So I guess that's all for today. Tomorrow we'll look at sections 9.2 and 9.3.